Laminar flow. Flow is equal to the change in volume over the change in time, and it's measured in litres per minute. So you can imagine a volume of a flowing fluid passing a fixed point per unit time. That defines flow. Now, if the fluid that is flowing is in organised laminae against a resistance R, then it will develop a parabolic flow profile with low internal friction and hence resistance, and will obey Poiseuille's law of laminar flow and also a hydraulic form of Ohm's law. So Poiseuille's law implies that resistance is proportional to the viscosity of the fluid, not the density. And Ohm's law implies that V equals IR, so delta P is equal to flow times resistance. This means that there's a linear relationship between pressure drop and flow, and the gradient of the graph is 1 over resistance. Now, both of those facts are true for laminar flow, but not for turbulent flow, and that has crucial implications about efficiency. So if we imagine a flowing fluid entering a tube, you can see that it actually takes a specified distance before the flow profile develops fully into a parabolic velocity profile, assuming the conditions are appropriate for laminar flow. So with this velocity profile, the central lamina is at maximal velocity and it tends towards zero by the wall. And that varies with the distance x, where velocity is equal to constant times x squared. So if we plot v against x, we can see that we get a parabolic graph because y is equal to kx squared. And actually the effective velocity of the flowing fluid is equal to half of this maximal velocity of the central lamina. Now this developing flow profile eventually reaches fully developed laminar flow, and the distance that is required after entering the tube for this is known as the entrance length.